Okay, differential equations, a brand new class, brand new textbook. Wow, we are in our very first section, 1.1. Chapter 1 is exceptionally short. It's the shortest chapter of the year. It's really an introduction to what differential equations can be like. And then we specialize quite a bit more on future chapters. But let's just get the ball rolling. You can look at our learning targets at the top. I can classify a differential equation. By the way, you'll abbreviate that very frequently with just a DE as linear or nonlinear. You could have a linear differential equation or a nonlinear. And then, wow, as we get to our first test, I can tell you already, I remember quite well, a lot of the problems that you'll have will be verification, showing that a particular function really is a solution for a differential equation. So as we progress, we're going to actually find those solutions, but for the moment, we can dive in and actually show that they are in fact true. So differential equations, a DE, it's an equation containing derivatives or a derivative of one or more dependent variables with respect to one or more independent variables. Generally, the independent variables in the past, we generally have represented them with X. Dependent variables, generally, we've represented them with Y, like Y depends on X. Of course, we can have different variables in those settings as well, especially as we get to applications. But in the past, you'd have functions like Y equals something. Y would be the dependent variable. It depends on what X is. So how do we classify? Well, three ways: by type, by order, and by linearity. Type, it's almost silly to bring this up, but it's important to let you know, we're in ordinary differential equations. Ordinary differential equations are where you have derivatives of one or more dependent variables with respect to a single independent variable, such as dy dx. dy dx. Partial differential equations, that's not what we're getting into. We're not going to deal with even one example like that. That's a 300 level class. And by the way, that's challenging. That's one of the hardest math classes that I remember taking in undergrad. Very, very demanding work. I remember having to do some of those problems, and it would be like a page and a half for one problem. Like, wow, just a lot of work. Partial differential equations are dealing where you have your differential equation involving partial derivatives like we just saw in multi. That's not really what we're getting into. We're not getting into that at all. But order, wow, classification by order. The order of a differential equation is the order of the highest derivative. So if you have the highest derivative is the third derivative, that would be a third order. If the biggest derivative, the highest derivative, is a second derivative, then it's a second order. Okay, so that's all we're talking about right there. And as you progress through the chapters, you might say, oh, now we're going to deal with second order and so forth, right? Linear and nonlinear, you can see that's really what we had for our learning targets. A differential equation is linear when two things are true. Number one, the dependent variable y and all its derivatives are raised only to the first power. Any derivative is only raised to the first power. You won't see any derivative raised to the second or third power. Second of all, the coefficient, whatever is multiplied to y or its derivatives, depends only on x, the independent variable. So I think we need to see some examples as to what is happening. Take a look at this first example here where we have 6x squared y double prime plus 5x y prime plus 3y equals 4. Notice that step 1 is satisfied. Y double prime, Y prime, and Y are understood to be raised to the first power. We don't have parentheses around them, raising them to a second, third, fourth power or anything like that. So Y and its derivatives are only raised to the first power. Second of all, look in light blue here. We have 6x squared, we have 5x, we have 3. Those coefficients only have x in them, or perhaps they have no variable at all, which would still be a function of x. You don't see a y in there. So if you meet those two criteria, you'd say this would be linear. But take a look at in the middle. Here is something that's not linear. And it's very important to see what goes wrong when you'd say, well, we don't have a linear differential equation. This would be a nonlinear. As soon as you see 6xy, y double prime, you know you're in trouble. Why? Because that coefficient, sine of xy, is not just with respect to x. It has a y in it. So that would be nonlinear. You can't have y in a coefficient. And I'm using that color to really make it pop out. Okay, so that would be a way to not be linear, to be nonlinear. Take a look at the next differential equation. Y double prime quantity squared minus 4y equals, it looks like I wrote 3 cosine x. The problem is you have y, or a derivative of y, raised to a power other than 1. You can't have a power of 2 for y or any of its derivatives. That would be non-linear. So that's just basic. By the way, I want to tell you too, on your first test, I'll have a little table where you'll have to identify whether some differential equations are linear or nonlinear. So very important vocabulary to talk about and very important concepts to be able to check. Okay, so linear differential equations are always and only ordinary differential equations. So if you meet the criteria to be a linear differential equation, you won't have partials, right? By the way, I only bring this up because, partials, they're a whole nother animal. But everything we're doing is just ordinary. Second of all, right here, a differential equation is nonlinear when it is not linear. That sounds kind of funny, but just want to make sure that everybody realizes that nonlinear means exactly the same thing as not linear. Okay? Well, here we go into potential problems. Any function y defined on an interval I and possessing at least n derivatives that are continuous on that interval, which when substituted into an nth order ordinary differential equation reduces the equation to an identity, meaning the left side always equals the right side, is said to be a solution, here. So, wow, here is the big question, wonderful question. Is y equals 1 over x a solution to this differential equation? And I want to point out to you, we're going to see so many of these. This is your differential equation. Clear as day, it's an equation that involves derivatives of y. So the question is that a solution? Well, let's check. First of all, when you look at y equals 1 over x, this is super important. I want to point out to you something super important. This function is not always defined, right? What can x not equal? 0. That means you are defined, now this is important, on the interval from -infinity to 0 or 0 to infinity. And you could only really have one of those intervals at a time, right? You could say, with continuity, you could say, well, look, either my function is going to be defined from 0 to infinity or from negative infinity to 0. So let's go ahead and see if this really is a solution. Here's what you're going to have to do quite a bit in chapter 1. Let's go ahead and take our derivative. Let's go ahead and take our derivative. Wow, one of the most famous derivatives you'll ever see. 1 over x, you guys remember what its derivative is? Yeah, negative 1 over x squared. Of course, that's x to the negative 1. You bring negative 1 down, subtract 1, you get x to the negative 2. So kids will say, how do you know if it's a solution or not? Here's what you do. You go x, but plug in your y prime. Plus, plug in your y. And notice what I'm going to write here. I'm going to write equals with a question mark. I'm trying to see if this is really an identity, if it's really true. So whatever y is, whatever function you're saying is a solution, replace that in the differential equation, plug any derivatives in, and then simplify. So what is x times negative 1 over x squared? It's negative 1 over x. And negative 1 over x plus 1 over x, what's that? 0. 0 equals 0. So what can we now say? Y equals 1 over x is a solution on one of two intervals. It's either negative infinity to 0 or 0 to infinity. If you had an initial condition, if you had a beginning x and a beginning y, initial condition, it would only be one of those two intervals. You wouldn't choose both. Okay, and we'll talk more about that next time. Is this making sense so far? What are we doing? We're just validating that this really is a solution. Let's go to page 2. And, wow, when we get to page 2, there are explicit solutions which can be solved for y. And that's really what we'll be dealing with extensively in this class. We'll be trying to find what y equals down the road. And then there are implicit solutions which cannot be solved for y. And we're going to talk more about that as we finish up this lesson. Notice, however, if we have this differential equation, 6x squared y double prime plus 5xy prime plus 3y. Ooh, here's my question to you. Is this linear or nonlinear? What do you think? It's linear. And kids will say, how do you know? Well, look, your y prime, your y double prime, they're only raised to the first power. And just as important, guys, just as important, we're going to say, look at your coefficients. Your coefficients don't have a y in them. Whatever's in front of a y or a y prime or a y double prime only is a function of x, never a function of x and y. So we could have a linear differential equation. By the way, what order do you think this would be? This is a second order. Kids might go, I beg your pardon? What tells you that? The highest derivative is a second derivative, right? So this is a second order linear differential equation. And all of a sudden they're saying, hey, would you look at this? This might be absolutely shocking. You could say, you know what? This thing is going to be a solution of y equals 0. Kids go, are you sure about that? Well, think about it. If y equaled 0, y prime would equal 0. Y double prime would equal 0. And it would be pretty easy to plug in for y prime, and y double prime is 0. 0 times anything is 0. And of course, you'd add that up and you'd get 0. Now, this is known as a trivial solution. We're generally not too interested in them. It's almost like a silly, like, yeah, of course that works. Y equals 0 is going to work. We're going to be more interested in other answers down the road. But it's important for you to mention and to see that you could get what's called a trivial solution. It's still a valid solution. For example 1, though, wow, another great test question. Verify that this thing right here, by the way, in chapter 4, you'll actually find this. You won't be told this. You'll find it. You'll say, hey, I worked it out. I know what this is. By the way, there could be other ones, too. I'll begin to plant some seeds for you. But, let's just say someone says, hey, I think this works. Y equals x, e to the x. And you're saying, here's a solution. Verify. Verify. Now, first of all, I guess what I want to tell you is that this thing is valid from negative infinity to infinity. There is no discontinuity. There are no breaks in the continuity of the function. So if we're going to talk about an interval of solution, and we will, we're going to say this is valid from negative infinity to positive infinity. Well, how do we verify? Tell you what, you better get a first derivative. Now, ironically, I said we're not going to be taking derivatives as much in this class. At least for right now, we will. That's kind of the funny thing. So we're looking here. What rule do you think we're going to use to take a derivative? Product rule. And we'll have a uv prime. Well, that's x, and v prime is just going to be e to the x. Then we'll have u prime v, and u prime v, well, that's just 1 times e to the x. And without too much work, you've got that. We doing okay? Guess what else we have to do? Take a second derivative. Now, here's where I know you guys are on your toes, and I want to help you out with something. So very often kids will say, okay, I guess I've got to do the product rule here. If you're really on your toes, you're going to say, I just did that product rule. You see what we're talking about? Don't get me wrong, you could go through it once again from beginning to end. That's fine. But the fact of the matter is, you just worked that out. You said, hey, when I took the derivative of x e to the x, I got this whole thing from that product rule. But then what? Don't forget, you also have to take the derivative of e to the x, and what's that? The e to the x. Look at that. So that's kind of a cool way to do it. And you could say e to the x plus e to the x is going to be a 2e to the x. And now we have to validate it. We're going to say, look, we've got y double prime minus 2y single prime plus y. And we're going to say, will that equal 0? Well, yeah. Look, y double prime is x e to the x plus 2 e to the x. Watch out here. You're going to have to distribute a negative. Your y prime is an x e to the x plus e to the x. And then finally, your y is actually an x e to the x. And the question is, is this really going to equal 0? Well, if it really is a solution, it will. You will have an identity, but we need to make sure. Let's just go ahead and validate this. We'll say, well, hey, distribute this negative 2 to both. We'll have negative 2x e to the x minus 2 e to the x plus another x e to the x. And the hope is, does this really work out? Well, look at this. 2e to the x and a minus 2e to the x. That just wipes out to 0. And then look at this. 1e to the x, x e to the x plus 1x e to the x is a 2x e to the x minus 2x e to the x. We get 0. It worked. It worked. Yeah. So here's what I want to point out to you. You're going to say y equals x e to the x is a solution on what interval? Negative infinity to positive infinity. There were no discontinuities. We don't have to worry about any value of x that would break the interval up. We doing okay? This is known as an explicit solution. So very often you'll see that we can solve for y. What about the implicit? Last one of the day. Verify this. X squared plus y squared equals 25 is an implicit solution of the differential equation dy dx equals negative x over y on this interval. Oh, wow, look at this interval from negative 5 to 5. Wow, they're even giving you an interval. Guys, look at this first equation, though. What is this the equation of? It's a circle with a radius of 5. You'd say, well, hey, here we go. I've got a circle, radius of 5. Wait a minute. If I'm looking at tangent line slopes, maybe you can see what's happening already. What's going to happen at 5? What do you think is going to be happening at the point 5, 0 especially? This tangent line is undefined slope. It's a vertical tangent line, right? Yes.
So it says x less than 5.
Correct. That's because if x equaled 5, our dy dx would be undefined. So that's why we can't include x equals 5 for this differential equation. Our tangent line slope, our dy dx, would be undefined. And likewise, right here at the point negative 5, 0, if you'd let y equals 0, even in that differential equation, you'd see that it's undefined. You divide by 0. Okay? But all the same, you might say, well, wait a minute. Okay, that's making sense, Mr. Dobner, but how am I to verify this? This seems so weird. The way we verify implicit is to go back to Calc BC last year and just do implicit differentiation, right? So it's really like a Calc AB or a Calc BC problem. What's the derivative of x squared with respect to x? 2x. What's the derivative of y squared with respect to x? Yeah, 2y dy dx. Very good. And what about the derivative of 25? 0. And then you could say, well, I'll tell you what, I'm going to minus a 2x. We're almost done. And then you could say, well, if I'm going to solve for dy dx, I'm going to divide by a 2y. And sure enough, these 2's cancel out. Wow, you'd have this for your derivative. This is a differential equation, actually. It's one that we arrived at with an implicit solution. The implicit solution, this circle, x squared plus y squared equals 25, solves this differential equation. So if they're ever asking you to verify implicit, it's really doing implicit differentiation like you did. And we could say also, this is 4, forgive me, we want to include this interval. It makes no sense to, have x values bigger than 6, or greater than or equal to 5, or less than or equal to negative 5. You must strictly be between negative 5 and positive 5. Yes?
Is there another equation that solves that for values outside of this?
Ooh, okay, so that is something to be investigating down the road. So lots of broad material as we're going to be looking at it. For right now, you're going to be verifying. If it's explicit, you just take its derivatives and work it in. If they say show it's implicit, you just go before. But yeah, it does beg the question, are there other solutions? Is our solution unique? That's a very thoughtful question that Alex just asked. And that's actually a major theorem that we're going to be investigating. How many solutions do we have? Is it unique? And so forth. So great thinking already, really doing an awesome job. Here's where we're going to go to page 10, and we're going to do 1 through 33, the odds. And we've got our brand new textbook. I've put a link in our textbook, in our Google Classroom, and you can get started on it. But that's our first lesson.